Assalamualaikum and a very good morning. Today, we would like to present our ECG 263 mini project. We are from Group 4F1 and our group members are Natalia Sira, Nur Dahlia, me, and Shafi Aina.
For introduction, soil can be classified according to its moisture content as solid, semi-solid, plastic, and liquid. Each state has different consistency and behavior, hence different engineering properties. The boundary between each state can be defined based on the change in the soil's behavior, which can be determined through Atterberg limit test. In this group mini project, students are required to conduct certain soil engineering tests that can be associated with soil engineering fundamentals, concept, and describe the soil in the terms of the moisture content of soil, field density of soil, compaction parameter of soil, percentage of different grain size, and soil classification.
The test study for our ECG 263 mini project are the maps, which is the location of the soil, are located near with our University Technology Mara Campus Samaran Luar, and the topography are flat topography. The characteristic of the soil sample are the textures, which is fine particle, feels sticky and smooth when wet. The color are brownish to red color, and the plasticity are easily molded and shaped when it's wet. The accessibility of our soil are easily accessed, which is closer to the road and the main entrance. For the space are quite big spaces in the infrastructure or in terms of buildings, our soil are far from any buildings and any machinery of the construction. For methodology of our mini project, there are three types of tests that we need to be conducted. The first one are Kolkata method, secondly dry sieving, and the third one are compaction tests. For Kolkata method, the apparatus that we needed are Kolkata, weighing balance, straight edge, canes, ovens, and lastly ramming rod. For the procedure, firstly, we need to clear the area of any loose soil and debris. Secondly, use the ramming rod to drive the core cutter vertically into the soil until the top edge of the cutter is level with the ground surface. Third one, carefully dig around the core cutter to extract it from soil without disturbing the sample inside. The fourth, trim the excess soil from the top and bottom surface using the straight edge to make them flush with the cutter edges. And lastly, perform all the terms or the calculations. The second test are dry sieving. The apparatus needed are weighing balance, set of sieve, cleaning brush, and lastly, sieve shaker. The procedure. Firstly, we need to write down the weight of each sieve as well as the water pane to be used in the analysis. Secondly, record the weight of the given dry soil sample. The third one, make sure that all the sieves are clean and assemble them in the ascending order of sieve numbers. Place the pane below the 200 micron sieve. Carefully pour the soil sample into the top sieve and place the cap over it. The fourth one, place the sieve stack in the mechanical shaker and shake for 10 minutes. And lastly, remove the stack from the shaker and carefully weigh and record the weight of each sieve with its retained soil. In addition, remember to weigh and record the weight of the bottom pane with its retained fine soil. Lastly, are compaction tests. For this compaction test, the apparatus needed are standard Protomold plus 1000 ml volume with reamer of weight 4.5 kg, extruder, paint, measuring cylinder, steel straight edge, weighing balance, and lastly, mixing equipment. The procedure. Firstly, we need to take about 5 kg of representative of dry soil sample, passing on 37.5 mm or 20 mm sieve. Secondly, add adequate water on soil sample to bring its water content to about 7% or less than the estimated optimum moisture content. Third one, clean the mold and the base plate. Fit them and record the mess. Fourth, apply oil on inside of the mold. The fifth one, attach the collar to the mold. Next, remix the mixture soil, compact it in the mold in 5 equal layers using the reamer at 27 blows per layer. Next, remove the collar and cut the excess soil with straight edge. The eighth step, clean the mold from outside and record its weight. Next, take out the soil from the mold. Keep a representative soil specimen from the middle of the mold for water content determinations. And lastly, repeat steps from 5 to 10 about 5 times, but with a gradual increments of water content each time by adding sufficient amount of water on the soil. In a normal case of compaction, the mass of the soil, which is weighed in step 9, is become heavier for the first 2 compaction stages, but it will become lighter after the 3 compactions due to the soil become more saturated.
So, this is result for moisture content. So, this is result for field density. So, this is result soil classification for sieving test. So, this is result for compaction with the graph, which is maximum dry density against moisture content.
As we work on our soil engineering project, we aim to evaluate the soil characteristics of a compacted area proposed for the construction of a community hall. Our tests included moisture content analysis, field density determination, compaction parameters assessment, and grain size distribution analysis. The results of these tests have provided us with valuable insights into the suitability of the soil for the proposed construction. We began by analyzing the moisture content of the soil, and we discovered that it was 12.26% for A, 12.5% for B, and 12.64% for C. This is an important metric since it impacts the strength and compaction of the soil. When the soil is compacted, it can reach its maximum density and stability when the moisture level is within the ideal range. Since standard equipment was not available, we had to create a core cutter procedure for the field density test. The results show a field density of 1.09 gram per centimeter cube for A, 1.25 gram per centimeter cube for B, and 1.18 gram per centimeter cube for C. These values are slightly higher than what we achieved in the laboratory compaction test, where the maximum dry density was 1.947 gram per centimeter cube. This discrepancy indicates that the soil in the field might not be fully compacted to its optimum state, suggesting that additional compaction might be necessary to enhance the soil's load-bearing capacity. The findings of the compaction test were very helpful. The maximum dry density obtained from the laboratory test was 1.947 gram per centimeter cube, and the optimum moisture content was determined to be 10%. Comparing these values with the field density results, the relative compaction was calculated to be approximately 95%, which falls within the typical required range of 90 to 95%. This indicates that the soil has been compacted adequately in the field, but there is still some room for improvement. In the grain size distribution analysis, we determined that the soil consisted of 82.33% of gravel, 17.48% of sand, and 0.19% of silt. The soil is classified as silty sand. This classification is important as it gives us an idea of the soil's drainage properties and its behavior under load. Silty sand typically has good drainage but can be susceptible to erosion if not properly managed. During our test, we took careful steps to get accurate results. For example, in the field density test, we inserted the core cutter gently to avoid disturbing the soil. However, we used some improvised equipment which might have caused small errors in our measurements. The findings from our test suggest that the soil in the proposed construction area is generally suitable for building a community hall. However, to ensure maximum stability and performance, further compaction of the soil is recommended. This will help achieve the desired field density that matches the laboratory maximum dry density, ensuring the strong and stable foundation for the construction. Based on our soil engineering project, we have determined that the soil on the proposed site has suitable characteristics for construction. Although there is room for improvement in field compaction. The moisture content of the soil is within acceptable range, ensuring strength and stability. Field density tests showed slightly lower values than laboratory results, indicating potential for better compaction. Grain size analysis confirmed good drainage properties, crucial for construction stability. Overall, achieving the recommended dry density in the field will ensure a stable and strong foundation for proposed construction. Our point of view on advantages of project implementation is first, practical learning experience. Students can apply classroom knowledge to real-world scenarios, deepening their understanding of soil mechanics and testing methods. Second one, skills development. Handling soil testing equipment and conducting experiments enhance technical proficiency and attention to detail, critical skills for engineering professionals. Third, real-world application. The project bridges the gap between theory and practice, allowing students to see the impact of their work on actual construction projects. Next, teamwork and collaboration. Working in groups fosters communication, cooperation, and conflict resolution skills, which are essential in professional environments. Next, problem solving. Encountering and addressing unexpected issues during the project develops critical thinking and problem-solving abilities, preparing students for future engineering challenges. Career preparation. Gaining hands-on experience with industry-standard procedures and equipment makes students more competitive in the job market and better prepared for their careers. Next, confidence building. Successfully completing practical tasks boosts students' confidence in their abilities to handle real engineering problems. Next is networking opportunities. Collaborative projects provide opportunities to connect with peers, faculty, and industry professionals, potentially leading to mentorship and job opportunities. Lastly, research and innovation. Engaging in experimental projects encourage a research mindset and innovation, prompting students to explore new methods and technologies in civil engineering.